In this video, we're going to continue our discussion of a sort of human resources application in which we can store data about employees, teams, and the entire company. And we're going to now approach this problem from a different angle. Rather than rely on Python objects stored in memory, which can't persist through multiple sessions or be easily shared across different clients, we're going to approach this problem from the perspective of using a database. As we learned in last week's lectures, databases are often used on the back end for storing and retrieving data as required by an application or program. One of the reasons for this is because we can have multiple instances of the program access the same database as, for instance, the grader does for your mini projects. They all access the same grades database for submitting and recording your grades. And also because they are persistent. So they don't disappear if the machine running the database shuts down or reboots. Now, we can imagine an analogy between the classes we defined in the first approach and tables that we would define in SQL. So we, for instance, might start off with a person table. And the person table would have columns for name, age, degree, and salary. And then maybe also an ID. We could then also have a employee table. Oh, well, let's actually skip back a little bit. A degree table where each degree has a level, an area, and an ID. That way, the person table, the degree can be a foreign key where we don't have to store the level and area of the degree as part of the person table. In the person table, each row just makes a reference to some degree ID, which matches up to a row in the degree table that gives us the remaining information about the degree. Likewise for salary. We could have an employee table that adds a production to each person. So there would be the person ID, which would match the employee ID, and then there would be a column of productions in that employee table. The manager table could also have an employee ID and a capacity. So we would be adding a new table for each class, and each table would probably consist only of, a couple columns. But by, as we learned when we were talking about SQL databases last week, by separating out the data into many tables, we reduce redundancy. For instance, since only some employees are managers, we don't need null values for capacity for all the employees who are not managers. We can have a managers table where there's only as many rows as there are managers. And that way we're only carrying around as many capacities as we have managers as well. So it reduces redundancy, and we can always join together data from several tables whenever we need to answer more complex questions. So that's the analogy. Each object or class that we defined is now going to become a table in our database. And we are going to use a module called SQLAlchemy to accomplish this in a particular way where there will be a mapping between the various tables and a set of Python objects that we can interact with as we normally would in Python. And this tool, SQLAlchemy, is what's called an ORM tool, which stands for Object Relation Mapping. We're interested in making a mapping between Python objects and relations, or tables, in a database. Or really a row in a table of a database. So an object is an instance of a class. A relation is a row in a table. And an object has a relationship with class, much like relation has a relationship with table, in that an object is a single instance of a class, and a table lays out a schema for its relations, or rows. So we're going to work through our previous example using SQLAlchemy to build this object relation mapping. And what that's going to let us do is have a persistent database on the back end that could be used by multiple client applications. But those client applications will be able to interact with the database as if we were working with simple Python objects. The price we'll pay is that the work to set up this object relation mapping is a little bit strange and definitely works kind of differently than the classes that we're accustomed to defining in Python. So we're going to import SQLAlchemy, and I've aliased this as SQL. Now, this is not a conventional alias. It's not like NP for NumPy or PD for pandas, where you will always see those aliases. This is just something I'm using for my own convenience in this notebook. And we're going to define classes for, as we did in our previous example. But what's going to happen is these classes will be based on a special object from SQLAlchemy called the declarative base. That's going to serve as our base class. And because we inherit from this base class, all of the classes we define on top of it are going to be tied into a SQL database via SQLAlchemy. That's what's going on kind of in the background of this base class. So I'm going to first, before we examine some of these class definitions using SQLAlchemy, I'm going to point out a few things that we'll encounter that will look different from class definitions we've made in the past. First of all, as I just said, all of our classes are going to inherit from this declarative base, either directly or through other classes. So for example, manager is going to inherit from employee, but employee inherits from base. So all of our classes in this object relation mapping are going to inherit from base. Secondly, all of our classes are going to have a table name variable. And this dunder table name variable links that class to a SQL table. This is again, this linking happens through this declarative base. Declarative base is expecting us to define this table name, which will specify the name of the corresponding table where objects of this class will be stored in SQL. We'll notice there's no init method for initializing attributes. Instead, our attributes will be declared as variables of type SQL column. Again, since we're constructing a database in the back end through this declarative base, the way in which we define the attributes of our class works a little differently. Remember, SQL requires typing of the columns. When we were learning SQL last week and we created a table, I can actually bring this up in the SQL notebook. When we created a table, we had to specify what kind of data, what type of data would be stored in each column. Therefore, in the classes that we define for our object relation mapping, we again have to define what type of data will be stored in the various attributes so that we can be compatible with SQL. So all of our attributes will be declared as variables of type SQL column, and those attributes will be typed. We are going to use integers and strings in our example. A sort of quirk of object relation mapping relative to regular SQL is that every table or class that we define will have to have a primary key. This was not true in regular SQL. For instance, our orders table had no primary key. When working with SQLAlchemy, each of our classes will have at least one primary key. Of course, this could just be an enumeration of the different objects / rows. And finally, whereas in when we created relationships in SQL with foreign keys referencing other columns in other tables, in SQLAlchemy, that'll be accomplished via SQLORM relationship, which is like this references, and foreign key, which is self-explanatory. So let's examine some of this code and try and get an idea of what's going on. So we'll start by defining a team class, which inherits from base. We'll be skipping some of the classes that we implemented in the Python example and going directly to some of their subclasses, just for the sake of brevity in this ORM example. But you would probably want to more or less closely follow the example as laid out in the Python approach previously for a well-normalized database if you were actually producing this for a serious application. But we'll take a slightly simpler approach for this example. So we're going to start by defining our team class. Team inherits from base so that we can get the attachment to SQLAlchemy on the back end. The name of that table, of the table on the back end where we will store our team relations, is just going to be called teams. And if we look through some of the other classes, we see this kind of pattern repeated. Class, employee, table name, employees. Class manager, table name, managers. The table name tends to just be the plural version of the class name. Each team is going to have an ID number, which will be an integer column in our teams table. And that column is going to be the primary key. Each team also has a name, which is another SQL column of type string. Now these are going to be attributes that we can interact with for each of our team objects. But they are also, the data is stored in a SQL database as a column. Finally, each team has members. And the members are going to be employee objects. So we're going to create a relationship with the employee class that we'll define soon. And we're also going to set some update rules for this relationship. So for example, if we were to delete an employee object from our data, from our database, we would want to also remove that employee from any teams that that employee was a member on. If an employee leaves the company and we remove their information from our database, we want to also make sure they're no longer on any teams at the company. So that's taken care of by this back populates. So the employee table is, anytime we make an update to it, it will back populate the team table. And the operations that will cascade to the team table, or teams table, are all operations. So any update to employee will cascade back to teams. There is, how did I know to do this? Well, I taught myself, basically, from the SQLAlchemy documentation. So there's extensive documentation for SQLAlchemy. It's not the prettiest website or necessarily the easiest to navigate, but right away we can see there's a thing on here that says read this first, object relation tutorial. So it can be useful to work through some of these simple examples to get a feel for how object relation mapping works. We see kind of the first steps we took right here. We created a declarative base, and then we defined a new table on top of, where the class inherits from the base. The table name is just the pluralization of the class name, and then we define some columns. Simple enough. There's also a section on building relationships, which describes how to set up this back population and using cascade rules. So if you're interested in learning more about ORM and SQLAlchemy in particular, I highly recommend also looking up the tutorials from SQLAlchemy's documentation. Now, where SQLAlchemy really starts to be useful is in what are called hybrid properties and hybrid methods. What these do is we can write Python code to effectively replace columns that we might otherwise have to store in our database. So for example, in our original, pure Python implementation, a team had a name, an ID, a description, and a manager. And each of these attributes we would normally think of as being stored in separate columns of a SQL database. So our team would have a manager column, or our teams table would have a manager column. There would be a manager for each team. What we can do with SQLAlchemy is, rather than store data in the database that we could otherwise figure out using Python code, we can write the Python code to figure out what should be in that column, and then call it a hybrid property, which will allow us to interact with our objects as if that data were stored in the database. But instead, it will just be calculated on the fly. So for example, we don't need to store a manager in the database for each team, because we can simply look through the members of the team, and if one of them is a manager, we return that member. So we can calculate on the fly who the manager is of a particular team. We also use this to implement healthy and production. So we don't need to store any of these values in the database. We can calculate them on the fly whenever we need them, based on relationships between different tables. Finally, we include a repr method, which doesn't really interact with SQLAlchemy in any type of way. This is just kind of what we would normally have as a repr method. So our team had a repr method like this, and that's in fact almost exactly what we have down here, just with a added team parens around the string. Now let's look at the employee class. Remember, team had a relationship with employee since members is populated with employees. We define all the various attributes we would expect an employee to have. We skipped over having salary and degree tables in this example, just to keep things simple. So there are salary amount and period, and degree level and area properties for employee, and those will each be a column in our employee database. Of course, many of the values in this column will be repeated, since there's only like 3 or 4 levels of degree people can have, as well as maybe 3 or 4 pay periods people could have. So we could reduce that redundancy by creating separate tables, and again, that's something we would want to do if we were writing a serious application where we had to optimize our database. Once we've defined all these simple kind of attributes that are just columns in the employee table, we notice 2 things. One, each employee has a team ID number, which is a foreign key from the team's ID number attribute. Also, there's a relationship defined here with the team table. So that updates to the team table, where operations with teams also backpopulate members. So if we happen to take a team and remove an employee from a member as a member of a team, that will update this team ID number in the employees table. I'm not going to get into what these mapper args are, but essentially it's related to when we have a class that inherits from another class, we have to define how what's called polymorphism works in SQL. I'm not going to get into the details of that, but again, this is something that you can look up in the SQLAlchemy documentation. It's the details about how to do this don't come up that often in simple applications. So you'll probably be safe just in following my example here. Again, we use a hybrid property to define the salary of an employee. This was in the salary class we had defined earlier. There was, as part of the repr method, we calculated a salary by taking the amount and multiplying it by the period. Here, to allow ourselves to kind of represent salaries in a uniform way, we have this hybrid property salary, so that we can on the fly calculate what the salary of a given employee is. Manager inherits from employee, so each manager object will have all of these attributes and the relationship with the team table. But additionally, managers have a capacity. There's also a hybrid method defined, which is very similar to a hybrid attribute, but since it's a method, it rather than interacting with it by just using kind of variable syntax where we have object.attribute, we'll interact with it using method syntax where we'll have object dot the name of the method, and then we can pass in any arguments in the function call. But the idea is essentially the same. This is something that we would have to store in the database and constantly update depending on what n is, or what we expect n to be. And that's really not what databases are made for. Databases are made for storing static information. So we don't want to be constantly updating this can manage flag based on changes in n. Rather, what we would like to do is just store the capacity and be able to on the fly calculate whether or not the manager can manage the number of subordinates that they are assigned. So we're going to run this. And now that we've defined our classes, it's time to actually create our database. We can create a database by first creating an engine for managing our database connections. So we're going to create an engine for managing connections to a SQLite database called company.db. I want to show you all the SQL that gets executed as we interact with SQLAlchemy, so I've included this echo equals true keyword. Now, we can create all of the appropriate tables that we've written classes for based on what classes inherit from our declarative base. So we can take our base and create all, and we're going to use our engine for creating these tables. So when we run this, we see a bunch of SQL gets executed to create our tables. We create the teams table, which has an ID and a name. Those are the columns we defined in the team class. We also marked the ID as being the primary key. And we see that reflected in the schema where we create the teams table. Likewise, we create an employees table. And we see all the attributes we defined, the primary key being set, and the foreign key, team IDN, being set to reference the IDN field in the teams table. Finally, we create a managers table, which has, again, IDN as the primary key, and it's also a foreign key referencing the employee ID number. In the manager table, that's exactly how we set up IDN. Notice that we don't have things like production, healthy, or manager in the employees table. Those are hybrid properties which we can interact with just like production. Oh, actually, this is not... Oh, sorry, this is the employees table. The things I was just describing are part of the teams table. So notice the teams table does not have production, healthy, manager, etc. as columns in the table. We can interact with those things just as if they were columns in the table, but they will be calculated on the fly. So I'm going to break the video here, and in the next video, we'll fire up a session to perform the object relation mapping and actually create some objects which will also become relations in our database.